Hello. Okay, in this video, I'm going to talk about conservation of energy as a concept, define what a conservative force is, what a non-conservative force is, and then talk about a definition for potential energy, which is where we're going with all of this. At the top here, I've got these equations, these definitions that we have, some of them definitions. So we have the definition of the network here, just our normal work equation with the net force as the force that we're integrating. We have the work energy theorem, that the network is equal to the change in kinetic energy for a system. And then we have the definition of kinetic energy here just as 1/2 mv squared at some given time moment. All right, so I want to extend some of this work, define some more stuff, and talk about how we can add a little bit more nuance to this equation, this work energy theorem. So let me define conservative force. And I'm going to define what a conservative force is through an example. So the example that I'm going to give of a conservative force is gravity near Earth's surface, which we've studied a little bit already. So if I kind of draw a picture here, if I imagine that I have some position above Earth's surface and some position above Earth's surface, and this is some initial position, some final position, using Z to indicate height above Earth's surface. If I have some object moving along some path between an initial and final position, then I can calculate the work done by gravity just by integrating the force of gravity dotted with the path length vector. So I'll plug that in. So the force done by gravity here is minus mg z hat. So defining up to be the positive z direction, or actually I'm going to use k hat here. So to be consistent with I hat and j hat, k hat being the unit vector in the z direction. And then dotted with dl. In dl, I'll write dx I hat plus dy j hat plus dz k hat. So I and j here would be sort of horizontal directions along Earth's surface, parallel to Earth's surface, and k would be perpendicular, or z would be perpendicular to Earth's surface. All right, so if I take that dot product, I only end up with the z component mattering. So I'm integrating from the initial z position to the final z position minus mg dz. And if I evaluate that integral, I get that it's mg times the difference between the final and initial positions with a minus sign. So the work done by gravity I could write as minus mg delta z, where z is just the change in the vertical position above Earth's surface. All right. So, okay, so this is under the heading of conservative forces. So what is a conservative force? A conservative force does work that is not path dependent. So for example here, nothing in this derivation of this expression, the work done by gravity, depended on the path that was taken. The only thing that determined what this integral looks like is that gravity points straight down, and only the bounds mattered. I could have some other path here. I could even have a wackier path if I wanted to, as long as I end up in the same, if I started in the same initial place and ended up in the same final place, the work done by gravity will be the same. The force never changes, so no matter how I get from Zi to Zf, I get the same amount of work done by gravity. So let me write this down. So work done by a conservative force does not depend on the path. Or I could say is not path dependent. that won't be true for every force, and we'll see an example shortly of this. And so this expression for the work done by gravity is true for any path from our initial and final spots. So in some sense, this it makes sense. You don't have to do any work on an object to move it horizontally if you're talking about the work done by gravity, but you do have to do work to lift it. Okay, so here's another example of a force we have not discussed yet. All right, another example here. Spring forces. All right, so let me draw another picture here. So if I draw a picture like this, see, okay. Let me say that there's a spring connected to a wall and also connected to a mass. And that mass M. There's an equilibrium position for the spring. So that is the position that the spring and the mass will naturally rest in. And let's say that's somewhere here. So I'll define this to be x equals 0. And there's some position x that in this picture I have pulled the mass away from the equilibrium position. And so just intuitively, what you would expect to happen is that the spring would try to pull the mass back in towards the equilibrium position. And the same would happen if we put our mass over here. We would be compressing the spring, and there would be some spring force pulling back towards the equilibrium position. So what characterizes the spring force, or one of the things that characterizes it, is that it always pulls back towards equilibrium. It's called a restorative force for that reason. So it tries to restore this equilibrium position. Okay, and as it turns out, the spring force, the magnitude of the spring force, can be written down as K times X. So how strong the spring force is proportional to how far away from equilibrium you've pulled the spring, which kind of makes sense. But it's also proportional to this thing called K. This is called the spring constant. So the spring constant is just a measure of how strong the spring is. So a larger K means more force when you pull away from equilibrium, which indicates a stronger spring. And the units of this, you can see from the expression, would be newtons per meter. So how many newtons of force do you get per meter that you've pulled the spring away from equilibrium? Okay, this is also called Hooke's law. Hooke's law says that the force of a spring is proportional to the displacement of the spring from equilibrium. Okay, so this is a little bit different than the force of gravity we saw above, because the force of gravity near Earth's surface is just a constant. This force is not constant, but we can show that the work done by a spring as it pulls or compresses is also conservative. So let's see that. So let's say that I've got some situation where I had the spring maybe start at this position here. So I'll call that XI. And then I pulled it out to this position here, let's say. So maybe the back of the mass started here and ended here. And I moved along the path that pulled the spring out from the initial position to the final position. And I want to know how much work did the spring do along that path. And I'm pulling out from equilibrium. So really this is a one-dimensional problem here. The only dimension I'm considering is the dimension along the spring. And we could think about how to generalize this into more dimensions. But for right now, we're just considering a one-dimensional problem from there to there, which is what I've called the X coordinate, the X dimension. 1. Okay, so the work done by the spring Well, that's going to be integrating the force of the spring dotted with the path length vector. So the force done by the spring is minus kx I hat. So in the negative x direction, as we pull out into the positive x direction, the force pulls back toward the equilibrium, so the force is negative, dotted with the path length vector, which is just this one-dimensional path length vector dx I hat, and we're integrating from the initial x position to the final x position. Okay, so we take that dot product, we just get minus kx dx, and you can prove to yourself that what you'll get if you do this integral is minus 1/2 k x final squared minus x initial squared. Okay. I did a couple steps there, but I'll just do it quickly like that. So this is the work done by a spring. Notice again that this has the character of not really caring how we got from the initial position to the final position. In fact, even though this is a one-dimensional problem, I could take many different paths to get from xi to xf. So if I have my mass that starts here, for example, I can go straight to here and call it a day. That's one path to get from xi to xf. I could also have started here, gone way past xi and come back, or way past xf, excuse me, come back to xf, and the work is the same. The force value never changes. And so the only thing that matters are the bounds, the value of the bounds. Nothing about the integrand changes depending on the path that I take. And so therefore the work that I get will always only depend on the endpoints. So this is true for any path from xi to xf. Okay. So that's interesting. So this is a force that it's not a constant force. It depends on the value of x, but you end up it ends up being a conservative force anyway. So that's an interesting example. Okay, so here's an example of a non-conservative force. So in opposition to conservative forces. So an example of a non-conservative force is friction. So the thing that defines a non-conservative force is that the work done by a non-conservative force will depend on the path taken from the beginning to the ending of a problem. So for example, let me draw yet another picture. So here's a picture of a mass that is sliding or being pushed around on some plane. Okay, so let's say this block has mass m. It has some initial x position here. So again, we'll define kind of the plane here to be the x dimension, x coordinate. And there's some final x position here that the mass ends up at. Something like this. Okay. All right, so how would we calculate the work done by friction between xi and xf? Well, let's take a particular path and look at it and compare it with a different path. So if I take a path where, this will be the blue path. So I start here and I go this way. So the mass just slides forward from xi to xf, and that's it. The force of friction the whole way will point opposite that motion. So there's some kinetic frictional force. And we should expect the kinetic frictional force to be described by mu k times the normal force. And so I can write that down too. So frictional force should be, the magnitude of it anyway, should be mu k times the normal force, which in this case is mg. And you can convince yourself that the normal force is mg if you want. So for this blue path, the work done by friction will be integral from xi to xf. I've got the force of friction is minus mu k mg I hat dotted with dx I hat. So the work done by friction, you can convince yourself, is minus mu k mg times this displacement xf minus xi. Okay, so that makes sense. So the force of friction is constant here, or at least we're modeling it that way. So what we end up with is just kind of the force of friction times the displacement. The minus sign means that the force of friction is pointing opposite our displacement. So all that makes sense. The larger the displacement is, the more work is done by friction. All that makes sense. Let me describe a different path. So if I take a different path in a different color, what color is good? Purple. Let's do a purple path. So if I have the mass sliding and going past XF and coming back to XF this way, so now I'm going to define a different point, like the furthest point it gets. I'll call this, I don't know, X naught. Okay, so how does this change things? Well, while the mass is sliding this way, nothing's really different about the problem from the blue, for the purple path versus the blue path, because the force of friction is the same. And so we're going to end up with an expression that looks a lot like the work done by friction for however long the block slides this way. But as soon as the block gets here and turns around, now the force of friction points back this way as the block slides back left. So the value of the force of friction changes, the direction of it changes. And that has a big impact on the way we calculate the work. So we really have to split this into two integrals. If we want to do it, we got to calculate the work done by friction for the purple path. There's two parts. The first is when it's going right from xi to x naught. This integral looks just like the one above. The force of friction there points left in the negative x direction, dotted with our path length vector. But now we have plus this other part of the work where we're going from x naught back to xf. And when that's true, now the force points to the right because the block is moving left. So it's a positive frictional force dotted with our path length vector, like that. So we can't really do the single integral here because the value of the force changes discretely when the block slides. All right, and actually, let me move this expression down so that it's connected. I don't know why I squeezed it over into the corner like this. All right. Okay, so let's do this integral. I think you might be able to see that it's going to be different, but let's work it out anyway. So the two parts of the integral, the first one, minus mu k mg x naught minus xi. And the second part, plus mu k mg xf minus x0. Let me recombine this in a different way that may add a little bit more intuition. So if we try to put it into the same form as above, so minus mu k mg times some displacement, that kind of looks like this. So we've got an x naught, and then minus an xi, and then I've got a plus x naught minus xf, just flipping the sign for that last part. So what is this saying? It's saying really this isn't a displacement, it's a distance. Because if you look at what's in here, we've got the total distance traveled by the block from xi to xf. This is the distance traveled as the block goes right from xi to x naught, and this is the distance traveled going left as the block goes from x naught to xf. And so you just get extra work done by friction if the path gets longer. And this is different than the forces we considered earlier in the video, gravity near Earth's surface and spring forces, because this work is path dependent. The work we did on the blue path was just less than the work we did on the purple path. And that's what characterizes non-conservative forces. So friction is an example of this. Other dissipative forces are examples of non-conservative forces. And because of this difference, we treat non-conservative forces a little bit differently than conservative forces. And I'm going to talk about that next. Okay, so let me define potential energy. So all of this has been working towards a definition for potential energy. Okay, so for conservative forces only, we can define potential energy. And we define a change in potential energy as negative the work done by a conservative force. And I'm writing W sub C just to indicate that we're talking about some conservative forces or all the conservative forces in a problem or something like that. So that is, we're defining a change in potential energy that is negative the work done by conservative forces, leaving out any work done by non-conservative forces. And so if we use our prior examples, the change in potential energy done by gravity near Earth's surface is mg times the change in the height above Earth's surface, just negative the work we calculated before. The change in potential energy for a spring would be 1/2, not m, k times the difference in the squares of the initial and final positions of the spring from equilibrium, just negative the work done by the spring before. And we can define expressions like this for any conservative force that we encounter. These are the two that we looked at in the video, so those are the two that I've written down here. So why are we doing this? Well, if we look back at the work energy theorem, it says the net work is equal to the change in kinetic energy. So let me split the network into two parts. There's the work done by conservative forces and the work done by non-conservative forces. So that's saying like this part would just be an integral FDL where the F there represents all the conservative forces in a problem. And this would represent an integral FDL where the force there represents all the non-conservative forces in a problem. But according to our definition, we can replace the work done by conservative forces with negative change in potential energy. So we're replacing just the work done by conservative forces there. And so if I rearrange things, I end up with an expression that looks like this. All right. So, okay, so this is a statement about conservation of energy. We're now defining energy more directly, and we're defining different kinds of energy. So we have this thing called kinetic energy, and we see that the change in the kinetic energy plus the change in the potential energy is equal to the work done by non-conservative forces. So let me unpack that a little bit. What happens if we have no non-conservative forces? In the absence of non-conservative forces, well, this simplifies a little bit. Then we don't have this term on the right, and we just see that the change in kinetic energy plus the change in potential energy is equal to 0. What does that mean? That means that the sum of these values never changes. I can have kinetic energy changing and I can have potential energy changing, but they always change in such a way to make the total change of this expression 0. Often, this will be called the change in mechanical energy of the system. And I can write this another way. So I can, instead of having a change in kinetic plus a change in potential, I can write this as the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. That is to say, if the sum of the kinetic energy plus the potential energy does not change, then I can take whatever the initial value of the kinetic energy was plus the initial value of the potential energy, and that will always be the same value. If I look at the sum of those quantities at some initial time and some later time, I'll get the same value every time. And this is what we would call the, this is mechanical energy at some final time. This is mechanical energy at some initial time. Okay, so this is a statement of conservation of energy. If there's no non-conservative forces, mechanical energy is conserved. What does mechanical energy mean? That means the sum of kinetic energy and potential energy. So that is the work done by conservative forces counts in mechanical energy. The way to think about what's happening here is that if you have a conservative force, if all you have is conservative forces acting in your problem, then you can always get that energy back out as kinetic energy. So if I throw a ball upwards and gravity is the only force acting on it, as the ball goes up, the potential energy increases, the kinetic energy decreases. But when the ball gets to the top and starts coming back down, then on the way down, I get back the kinetic energy from the potential energy of gravity. So in a conservative force, you can always get that kinetic energy back out. You can turn potential energy into kinetic energy. That's not true of non-conservative forces. I want to show you an example of how to use this expression of conservation of energy. So give me 1 second to get that set up here. Okay, so in this problem, I've got a block up here on a ramp. It's a 1 kilogram block. The block is released from a point that's 1 meter above this flat plane down here. At the end of this plane, there's a spring. And let's neglect any frictional forces here. That means that there are no non-conservative forces, and we should expect the mechanical energy to be conserved. So that means that the value of the energy at any given point should always be the same. And I could write that like this. So this is always a constant value. If I take any point in this problem and I sum up the value of the kinetic energy and the potential energy, that will be constant. So how do I do that? Well, it depends on what I'm looking for. So the question says, how fast will the block be moving at the bottom of the ramp? And how far will the spring be compressed? So what will happen here is the block will speed up as it goes down the ramp, reach some constant speed on the flat, and then hit the spring, compress it some distance. And then it will probably repeat this process forever. If there's no non-conservative forces, then you can expect this process to just like repeat forever. But all we're looking for is how fast will the block be moving at the bottom of the ramp and how far will the spring be compressed. So there's a few different spots that we're looking at. One spot would be down here, or I guess I should say the first spot is up top. So this is spot 1, I'll say. Down here, after the block has come all the way down the ramp, is on the flat. That's spot 2. And then there's some spot here where the spring will be compressed some amount. And that's spot 3. Let me name some variables. So at the bottom here, there'll be some velocity. I'll call that V naught. And there'll be some compression of the spring here at the maximum compression spot. I'll call that X naught. Okay, and what we can say is that at spots 1, 2, and 3, the total mechanical energy will be the same value. But as it turns out, we know what the mechanical energy is at the top. So at spot 1, we can write down the kinetic energy at that spot plus the potential energy at that spot. All right, so the kinetic energy at that spot is just 0. We're releasing this block from rest. The potential energy at that spot is mgh. So notice before, this is a little bit of a subtlety. Notice before we were defining changes in potential energy, but we can conceptualize that change as a change from the potential energy at one spot to the potential energy at another spot. So if we define z equals 0 here at the bottom, then the potential energy at this spot 1 up here is just mgh. If the block goes all the way down the ramp to the bottom, the potential energy down here will be 0, making the change in potential energy from 1 to 2 negative mgh, as we would expect. We could define this 0 point to be anywhere we want. I've defined it to be the bottom of the ramp for convenience. I could put 0 at the top if I wanted. I'll get the same result. In fact, that will make the total energy 0, which is fine. There's nothing physical about the total energy value. The only thing that's physical are changes in energy. And we'll get into that a little bit later. For now, know that I've defined 0 for height at the bottom. That makes potential energy 0 at the bottom. And at spot 1, the gravitational potential energy is mgh. There's no spring potential energy either. The spring is just sitting here, not compressed. The block's not on the spring, so we don't have to worry about that. So the total energy here is just mgh. So it's 1 times, let's take g to be 10, because that's easy and nice. And the height is 1. That makes the total energy, mechanical energy, 10. All right, at spot 2, let's do the same thing. What we know is that no matter what we get here, it's going to be 10 joules. There's no non-conservative forces, so the mechanical energy is conserved, and the total value of energy will always be the same. All right, so the kinetic energy here is something. It's 1/2 mv naught squared. We don't know v naught. There is no potential energy here because we defined this spot to be height equals 0. So there's no height for the block at 2, so there's no gravitational potential energy. And there's no spring potential energy because the spring is not compressed. So we can solve this by saying 10 joules equals 1/2 times 1 times v naught squared. So root 20 equals v naught. All right, so that was part A. That was nice. At spot 3, we can do the same thing. Kinetic energy at the third spot plus potential energy at the third spot. That will still be equal to 10 joules because energy is conserved, or mechanical energy is conserved. At the maximum compression of the spring, the block stops. because that's the furthest it gets on the spring before it starts getting propelled outwards by the spring. So there's no kinetic energy. The potential energy is 1/2 k x naught squared. Using the same kind of logic we use to define the potential energy at a single spot for gravity, rather than a difference in heights here, it's just the single height with a clearly defined zero. So there's a clearly defined zero here. It's where the spring has no compression. And so the potential energy here is just 1/2 kx naught squared. So that means that 10 joules equals 1/2 times K, and I defined K, or I said that K is 20 newtons per meter here. 1/2 times 20 times x naught squared. And I cooked the numbers so that 1 meter is equal to x naught. But what was nice about this is we didn't have to know anything about the way that the block got from point 1 to point 2 to point 3. We just had to write down what the kinetic and potential energies were at those points and use this conservation property to solve for what we wanted. So that's really convenient, and that points to the strength of this as a problem-solving approach that we'll continue to exploit as we go. So I hope that was useful, and I'll see you all soon. Bye.